So what we wanted to do is something different. So our colleagues at Harvard National Lab, they simply took a strip and they made holes in it. And this material is niobium. And so this experimental configuration is something between a single ring configuration and a network. It's in between. So in this case, the coherence length is much larger than the width. So we do not have, and it's also low TC material. So current fluctuations are not important here. And they also no effect due to weak links, because that can also induce superconducting insulator transitions and can lead to this huge amplitudes. So what they found was the following. Here we plot the resistance versus magnetic field for different temperatures. And you see here those little bar streaks here. But what you see is that it depends, the amplitude of it is strongly influenced by temperature. That's part moving. So you see clearly here, so I can climb up, and that means vortex exit. I go down here, no vortices in here, then vortex start enter here. You see it enters, that's when I'm at the top, and then it sits here, and then when I go here, it leaves. While in this case you see a continuously entering and at the same time exiting vortices, which corresponds to this situation. Good. So that's the theoretical explanation. That's the degree of experiment. So before I showed you the resistance calculations for different temperatures, but those people also did measurements for different currents. You also see that when the current increases, when I go from black to this triangles, you see that the amplitude changes. That's what I showed you before, that you can get a similar effect by changing the temperature and the same origin. Thank you.
Head of the group, and a PhD student, David, is here too. Maybe you had the opportunity to speak to him yesterday. He was in the poster session. And this is Wagner, is our PhD student who looks like, oh God, I missed the deadline for the conference of people. So we have also some external collaborators who are from the condensed matter theory group of the University of Utrecht in Belgium. Professor Francois Peeters, who is called now, and Professor Milosevic is also here. And so let me just tell you a little bit more about our city or our state, Ceará, and the city is Fortaleza. Our university is here. You are currently here in the city, so it's like a 1-hour flight if you want to visit our department someday. And these are some pictures of the city there. It's kind of similar to the city. Yes. So, okay, let's talk more about the world. Let me give you a brief overview of what we know already about vortices in superconductors, and then I will give you some idea of why we are trying to study interband interactions between vortices in multi-band superconductors today. So, first, what can I say? There is this theory of Leão and Nano from the 50s, right? Where you have a phenomenological theory of superconductivity, and these are some terms that appear in the equation. There is this Gibbs energy, this is Gibbs free energy. This is a fourth order expansion in Cooper pairs density. You know this very well, I suppose. So this is a kinetic energy of the Cooper pair density. This is the magnetic field energy. And with this, you can construct a functional of this psi and of the vector potential. And with some manipulation of the equations, you can define some parameters, which are the well-known coherence length, which is like the width of vortices that appear in the superconductor. Like it's the size of the core, actually. And the lambda is like a penetration depth of a magnetic field penetrating this. And with this, it was, we were able to understand what happens in some different types of superconductors. Because some of them, as you increase the magnetic field or the temperature, you see this kind of phase diagram here where you have superconductor and normal states here. This is like a line with a phase transition here, right? And then in the type 2, you have this mixture of normal and superconducting states where you have these vortices. And this was, we were able to understand where you can get this result or this one when you get this psi or lambdas in your material, superconducting material. So this was something like that. We know that there is a parameter lambda and psi that I introduced it to you in the last slide. So with this we can divide them. You have this kappa, right? And then the type 1 superconductors happen when this kappa is lower than 1 over square root of 2. And we can say that here we have kind of a vortex-vortex attraction. Because even if there is a vortex appearing there, there will be another one and they will sit together and they will become like a normal domain. So there will be no single vortex there in theory. So this is for type 1 superconductors. For type 2, you will have a repulsion between vortices. And because of that, you have this triangular lattice of vortices. And this was very well known in the past. Many people saw that in experiments. For example, there's this one from 88. There you see a very nice triangular lattice here. And this other one also in 2003 from this group. And so, okay, until here we knew everything that happened. I mean, we were quite used to the theory. But then there was a very controversial result that appeared a few years ago, which was this one by this group from Leuven, right? And then in this one, this is it doesn't match neither with these cases here, nor with a type 1 superconductor. It actually shows some results or some position of vortices that form like some pairs here or some domain like that. So this was very weird if you take into account only this theory.
And then again, if you look on the low temperature behavior, it is not anymore exponentially saturated, it shows clean kind of behavior. So let's see just by looking on the temperature behavior of the neon widths. At a low temperature, you could already say if you have nodes, have no nodes, for example. The next story is the field dependence of lambda. Again, if you have the S-wave superconductor is a gap which will be open, you shouldn't expect any dependence on lambda to material. However, in the case of node presence, just as schematically shown here, I mean, you have turning surface and you have nodes there. Then what happens as soon as you apply magnetic field, you have additional focal length, which is the velocity, and as soon as you go slightly above the nodes, you have excitation above the nodes, and then you have so much excitation of the place, and you are losing the coherence, you are losing the superconductor moment state. And just a simple calculation shows that in this case, the superfluid density should scale as a function of field as a square of the field ratio of plus. So this is just a simple mathematics.
Independent slide, the number that line because
Sorry?
not too sure that dependence is the equation. Independent because it is point line must.
Okay, at the moment, the principle is independent on which type of nodes regarding the temperature behavior. As soon as you have nodes, that means you have a gap which is zero on the nodal position. And any temperature which is not zero would already excite your quasi-particles above these nodes, and then you lose again the coherence. That means you will think about superconducting systems. And probably all of you know this famous graph where Hofner author just shows the dependence of the superconducting gap and the super gap as a function of something for various superconducting materials, and there are the combined measurements of RPS, of STM, and many things around and so on and so far. And what they show that the superconducting gap and the material gap has completely different behavior. One is showing linearly a function of coping, and the second one is showing dome-like shape, which is more corresponds to what you see from the screen. And we have more or less constant value. I mean, this is between the gap and the TC in this case, and it is not constant anymore. And there are two scenarios which are still discussed in the literature about what is Silver gap doing. It is precursor superconductivity of Silver gap and the superconducting gap are just two distinct phenomena. So what we did actually ARPAS and MUSA experiments on the same samples. And we were trying to combine the angular integrated quantities which we obtained from the ARPAS experiment of angular result. So we see close to the nodes, we have mostly the characteristic because the superconducting response is really strong. While close to the antinodes, it almost vanishes. So you don't see any weight, any coherent weight close to the antinodes. You can see somehow it looks like that they don't like each other. And if you go even further and plot just the weight in the Silver gap state and weight of the coherent state, there is a clear anti-correlation. I mean, if you have very small weight from the coherent state, then you have very high weight from the Silver gap, and vice versa, you have high weight from the coherent state and very low weight from the Silver gap. So this is just ARPAS stuff. And now let us go to the measurements of the superconducting density. Here I show the measurements of the width of the near line as a function of temperature for three different doping, underdop, optimally and the overdop. And from this part of the slide you see the mean time spectra. This is where the zero field. This is in transfer field, above this is the lowest. The red point corresponds to the measurements above the superconducting condition temperature, and the black one below the superconducting condition temperature. So what is really important that all of our samples are non-magnetic, because zero field above DC and below DC are just the same. There is no magnetism appearing as soon as we pull down the superconducting condition. What is also clearly seen that as soon as we go below TC, we have additional damping, which is caused by appearance of the vortex lines. So as I told you before, this is just an indication of the vortex lines that we could obtain the width of this distribution, which is plotted here. Now, this is anti-magnetic. I mean, with the bulk ions, we always measure in the vortex state. We could not measure in the Meissner state because in the Meissner state we have no field, I mean just streaming on a distance of lambda, which is too small.
To do this pyramid table, we compared to put cobalt in RMS level sample and see if incident will be used or how the ground state of this material will change. Now, first of all, we got to use nominal and experimental consideration by actually very close, not just in very close, very different from what you saw over there in the Now, unfortunately, there was another surprise with us. So we went up to 6% of cobalt in this material, and what we saw that actually all these samples, these ground samples, are in collapsed thermometers. And it's proven for one of them, it's for 5.9%, it's proven by experts. So if you just use as ground sample, everything is right, but cobalt goes in, you are ending up in collapsed thermometers. Now, with our exercise with pure calcium parameters, we ended on that anemic might play a role in the game. We checked that we are much better off with more than 5 days anemic just to show that we have something. So here is an example of what happens if you take different cobalt concentrations and then move all of them at 350 forward. So first of all, structural velocity transition does move. Second of all, you are getting signature of superconductivity. It's actually somewhat reasonable, nice signature in voltage. Resistance, I have seen better resistance transition, but still they're reasonably sharp, really resistant. What gave us a little bit good feeling is that we did have clear feature in heat capacity with a jump in specific heat consistent with other iron earth sites. But that's not, that's, I'm going to look aside. It doesn't mean we're getting a delta CP over ground C equals to 1.43.